Okay, today's topic it's called design of beams, but it's not exactly design. I wouldn't call it design in the sense that you're going to go out and figure out how tall to make a beam and how thick to make the flanges and all that kind of stuff. That would be a different topic. There are some web work and even sometimes test questions where maybe you're given a really simple beam like a rectangle and you got to figure out how tall it needs to be, something like that. Today, instead of design of beams as what I would actually call this, I would call it selection of the right beam, selection of beams. So you've got these charts full of beams, W8 by 80 and all these things. And which one do you use? That's obviously you could probably use the biggest one, but usually that means more cost. And it's probably more than what you need. But, are you sure that even it would work in your scenario? So what we're really going to talk about today is selecting the proper beam. So, and proper in this case means basically two things. It means that the beam is going to hold up under whatever factor of safety you apply. So maybe you want it to have a factor of safety of 3 against yielding, and you know what material it's made of. So maybe that's one criteria. And then the other one that if there's multiple that can do that, then the other thing would be what's the cheapest beam that can fulfill this factor of safety. In our case, we don't have price information for these beams. What we're going to use instead of price information is weight. So in general, a lighter weight beam is going to be cheaper than a heavier beam. Cheaper to buy because it's less material, cheaper to transport because it weighs less, cheaper to put in place because it weighs less. So it's not necessarily true, but in general, cheaper and lighter weight are equivalent, and heavier and more expensive are equivalent. And so we do have information in the beam's name, W10 by 70 or whatever it might be. We have the information about how much it weighs per unit length. So we're going to use that combined with a new term, S, which is in the chart. S is called the section modulus. And if you remember our stress equation, sigma equals negative m times y over I, that equation will calculate flexural stress for us in a beam then bending. And that's generally the thing that we're going to use to determine if this beam is safe or not, if it has a certain amount of stress or lower. There are shear stresses also that can cause beams to fail. In this course, we're not going to look at those because they're generally not the failure mode, although they can be. But if you're mechanical or civil engineering, then you'll take some courses after this one that will look at how to calculate those shear stresses, because you do need to know about those if you're designing a beam for real. But in general, flexural stress is how these beams are going to be most limited. And so we can calculate that, and we know how to get, that's the bending moment in the beam, and that we go and either draw the shear and bending diagram and plot the bending moment, or we know exactly where the maximum bending moment is in the beam and we just calculate that. So we can get that, and it changes from one end of the beam to the other, and we're looking for the maximum value for that. But these two, Y and I, they don't change. They're constant for any given beam. So for one beam, assuming that it stays one shape on one end of the beam and stays that whole shape through the whole length of the beam, which is pretty normal. Normally beams don't change from an I beam on one end to a T beam on the other end, and they don't really do that very often. So these two things, Y and I, are pretty much constant for a single beam, and they're combined together to create this section modulus. So section modulus is the combination of I divided by Y equals S equals the section modulus. And this thing is listed in those charts. So we'll have to get one of the charts out to look at this, but S is one of the columns in the chart. And so if we make I over Y equal to S, then we can rewrite our equation here. Now this one does calculate maximum flexural stress. So because you can put other values in for Y. So you could put the top of the beam or the bottom of the beam or anywhere in between for Y. So when you combine them in a way to make S, the section modulus, it's going to do sigma max. So the maximum flexural stress, wherever that is in the beam cross section, is going to equal M over S. And a lot of times you drop that negative sign because you don't necessarily know if it's the top or bottom of the beam. It's just the maximum magnitude of stress. So a lot of times in this equation, you don't have the negative sign because you have to figure out was this tension or compression based on other things. You can actually use this equation. If you have a problem that asks you just find the maximum flexural stress in the beam, you can use this equation and use S out of those charts instead of Y and I in the equation, and just use S in your maximum bending moment, and it'll calculate the flexural stress for you. But it will be the absolute value of it. You won't necessarily know if it's tension or compression without looking at the beam and the bending moment. So anyway, we can use this. Let's go look at one of these charts again so we can see where we get values for S. Let's see, so I have some in here. Down, nope, here. Let's see, we've done a W and a WT. Let's see if we have any others. We have C and S. We'll use an S. S is a standard flange I-beam. So W was a wide flanged I-beam. S is a standard flange. So basically, the flanges are smaller than they would be. And kind of, if you remember the picture, let's see if we can open the wide flange one. So here's the wide flange. See how the picture, the flanges are kind of wide. Here they're kind of narrow. So they're both I-beams, but S's are standard flange. They have smaller flanges than the wide flange ones. So let's zoom in a little bit on these. All right. So C under this column, XX and YY. Also, the YY also has this if the beam is loaded sideways. There's this S column, and it's units of inches cubed because you would be dividing Y over I, or well, I over Y actually, to create inches cubed. And you get this number. And so this number is the section modulus for any of these beams. So what we would do is, and in general, remember the beams are smaller at the bottom. So down here we've got a 5.7 pounds per foot. And at the top we've got 121. They're not universally that way. There's some where a lighter weight beam, let's see if we can find one here, these two, there's a lighter weight beam above a heavier beam, but they're different, one's a 12 and one's a 10. So there are instances where lighter weight beams occur above heavier beams in the chart, but in general the trend is lighter weight is at the bottom and heavier is at the top. But we don't know which one we want. Let's say we know we want an S beam. So that's all we know. We want an S beam, standard flange I-beam. And we would need something. Let's say that we have a diagram of a beam, and it needs a reaction. Oh, that's kind of big. Make that smaller. Going to have a pin. Let's put the roller over here so it's got a little cantilevered section in it. And let's put a distributed load over here. Let's not put a concentrated moment on this one just because that's not really what we're trying to do. We want to design this beam. We do know there's going to be an I-beam. We've chosen that, so we'll draw in, make it look like a I-beam from the side. And we know it's going to be an S. So standard flange I-beam is wanted. And let's say that we want a factor of safety equal to or greater than, we may not actually get exactly the factor of safety as long as we have at least this number. Let's say we want it greater than or equal to or greater than 2.2. And let's just say, now remember in our charts here, these numbers, it has a weight in it. So these numbers, we have to, let's see if it even says, it doesn't even say, but it says courtesy of the American Institute of Steel Construction. So I have to assume these are steel beams. And in general, all the steel beams are going to be made more or less with the same density. So these can be that structural steel, kind of generic material in our charts. It could be one of the different carbon concentration steels, but it's not like a stainless steel or something like that. So assuming that it's just a regular old steel, mild steel of some kind, then these numbers represent the weight per foot. In general, though, it would still be the same relative number if we had a slightly different type of steel. The number here, 31.8 or 35, would still be smaller and larger for those two beams. It just may not be exactly 35 pounds per foot if we had a different alloy of steel. But in general, these numbers will be correct. We're going to assume that it's just our plain old structural steel. So we need that chart, material properties. So this one here, structural, whoa, wow, it's crazy. This one, I didn't specify if it was in tension, compression, shear. Well, we know that it's tension or compression for a flexural stress. I didn't specify if we wanted to do elastic strength or ultimate strength. Remember, elastic strength is the number, if I exceed this 36,000 KSI, 36,000 PSI, 36 KSI, if I exceed that much stress in the in tension or compression, this B means that they're the same value. Then I have yielded this beam and it will no longer return to its original shape. It'll be permanently changed. And so that's probably the number I mean when I say factor of safety greater than 2.2. To be more clear, it might say if it was a problem on an exam or web work, factor of safety greater than 2.2, and then it might have some clarifier against yielding or elastic failure. Or it could say against fracture, you know, if I wanted you to design this thing against the ultimate strength. Although in general, you don't design machines to operate where they don't fracture. You generally design them to operate where they don't yield, because usually once something's yielded, then it's not going to work very well the way you intended it to, because it's all deformed out of shape. So it's probably not going to do what you meant. So most of the time, you're going to be using the elastic strength or the yield strength here. So that was 36. So sigma y for this structural steel that we'll assume this beam is made from was 36,000 PSI. And we want a factor of safety of at least 2.2. So that'll mean our allowable, how much stress we'll allow, is going to be 36,000 divided by 2.2. That's a weird number. 16,363.6 PSI. So if we exceed that much stress in our beam, then we have yielded it. Well, we haven't necessarily yielded it. We just have gone too close to yielding. We wanted a factor of safety of 2.2, so we didn't really even want to be close to yielding. And if we exceed this stress, then we're getting close to yielding, and it makes us uncomfortable, and we don't like that. So let's put some forces on here and figure out how to design the right beam or select the right beam for this load. So let's make them pretty large forces. Let's say that this is 6 kips, and this is 3 kips per foot, and this is going to be 1. Oh, that's kind of big too. Let's make that smaller. 1, 2, 3, 4, 6 feet, and 1, 2, this looks like 5 feet. So it's 11-foot long beam. 5 feet of it is kind of cantilevered over there, and then 6 feet of it is supported on both ends. So we'll say that point A over here was a pin, and point B over here was a roller. And I just didn't draw that there's also the possibility for a horizontal reaction at that pin, but it's going to be 0 for what we're doing here. We need to figure out these two reactions. So let's lump the distributed load. It's 3,000 pounds, 3 kips. Let's leave them in kips for this one. 3 kips, but it's over 6 feet, so that's 18 kips total. Go ahead. Oh, yeah. Oh, should be. Well, it is now. All right, so this thing, I don't know where my purple color went. Get up there. All right. We'll lump that together as 18 kips, and it'll be set over 3 feet. And we'll write a moment equation about A. We'll say that clockwise are positive, and so we have 18 kips, and that is 3 feet moment arm for it. We'll have BY, which is going to be this guy. This will be AY. So minus BY, that has a moment arm of 6 feet, and then 6 kips has a moment arm of 11 feet. And those all need to add to 0, and we can solve for BY. Let's see, 18 times 3 plus 6 times 11 and divide by 6, 20. So 20 kips for the reaction at BY, and then we can do summation of forces in the Y direction to get a value for AY. So AY goes up, so plus minus the purple just concentrated force, 18 kips, plus BY, which was 20 kips, plus the 6 kips at the end of the beam, which maybe that's point C, so plus 6. So we have 26 going down, so we need, oh, and we also have 18 going the other way too, so we actually have just enough. What did, oh, right. And that should be kips, not just 6. All right, so AY is going to only be 4 kips. All right. So now that we have those, we can draw our shear and bending diagram. And again, on an exam, I'm not going to have you draw the shear and bending diagram. Normally how this problem shows up on an exam is you start with the shear and bending diagram already drawn, and you just have to pull the right information from it to start the problem for designing the beam. You'd probably have to go look up the material strength, apply your factor of safety and that part, and then figure out what the right maximum moment is, which is no trick to it. It could be that I'd create a beam where it has a positive bending moment and a negative bending moment in the same beam, and all you're looking for is the maximum magnitude. You don't care if it's positive or negative. Most, actually, as far as I know, all steels, unless we get into the special ones, let's look. Well, so there is one in here where it matters if it's tension or compression for steel, but all the others have the same strength in tension or compression. So if it mattered, then it would make a difference on if it was like a beam where it was a T shape and the tension and compression were in different parts of the beam, and sometimes it has this one apparently is stronger in compression than it is in tension, so it could matter. I'm not going to give you that on an exam. That I don't know if it shows up in web work or not, but on an exam, I'm not going to put you through all of that to figure out. So you're just looking for the maximum absolute value when we go to find the correct beam to use. So let's put our guidelines in here. We don't need too many this time. And let's say that let's put our 0 axis for the shear somewhere right there. And these are going to be in units of kips. We start at 0, and then let's zoom in on that so we can see what's going on. The first thing that happens is AY, which I didn't write down, but I think it was 4 kips, and BY was 20 kips. So we have 24 going up and 24 going down. So it looks like we're going to go up 4, then we're actually going to go down. So these kind of need to be pretty big units here. Let's make them units of 10. Mainly because we need to get down to, we can probably get better than that, but it's okay. Actually, I guess, no, they can go 5, 10, and it'll be okay. And -5. -10. That'll be okay. If I was more interested in the shear diagram, I might make it larger just to have more detail in there, but we're not so much. So we go up to 4 right in there. Then, so at 4, we're going to encounter the distributed load, which gradually loses 3 kips per foot for a total of -18. So 4 minus 18, whoops, 4 minus 18 gets us down to -14. I guess I need to draw the -15 mark on there. So -14 is somewhere in there. And the distributed load that we have on this part of the beam is evenly distributed, so it's a constant slope over here. So and it's negative because the distributed load is pushing downward on the beam in our negative y direction. So it'll be something like that. Then we have by. We're sitting at -14. By is +20, so that gets us up to 6. So 6 will be maybe right there. So this has got a very odd shape, right? Compared to what we've been doing anyway. There's no change in shear until we get to the end of the beam, and there's a 6 kip load at the very end. So we'll just go horizontal to the end, encounter the -6, which gets us to 0, and we have a shear diagram that looks something like this. We do have one of these triangle areas where we need to figure out where exactly does it cross the x-axis. So it has a height of 4, and this distributed load had a slope of -3 kips per feet. So it has a height of 4 kips, -3 kips per foot. So 4 divided by 3 means that it takes 1.33 feet to get from 4 to 0. And so we know the base of that little triangle, which means we also know this one is 6 minus 1.33, 4.67 to there. Then we can calculate this area. 4 times 1.33 divided by 2, so 2.66. The units on that would be kip feet, which makes sense for bending moment. This one is 4.67 times, it has a height of -14, so times 14. And it's a triangle, so we need to divide by 2. So it has a height, or well, an area of -32.69. This one has a height of 6, a base of 5, so it has 30. All right. So I have to zoom back out to work on where we're going to put our bending moment. This one didn't have any concentrated moments in it, so we don't have to worry about that. I'm going to put this bending moment 0 point right in there, and we'll try and get all these visible. So this is moment of 0, and the units are foot kips, kip feet, whatever order you want to put those. Normally you put kip feet or whatever, but normally you put foot pounds. So although foot pounds normally is talking about a torque, which these are not what we're going to call torques. They work the same though. So this first, we start at 0. The first area is a positive 2.66. Oh, and then we're going to go down 32. So we need to have these as big as we can. But let's make these maybe about 5. Yeah, let's do 5, and then -5, -10, -20, negative. Oh, what am I counting by? I don't know. 15, 20, 25, -30 will be off of our chart. All right, something like that. I could have moved it up higher, I think, but this is what we did. So this little line, let's go ahead and put this reference line in so that we can see it. All right, so somewhere in there, we're going to go up to 2.66, which is right in there. And it's actually curved. At this point, it's 0 shear, so that is a horizontal slope in my moment diagram. So it's going to kind of, oops, with that, kind of do something like this Maybe you can tell it's curved. And then we're at 2.66. We're going to subtract off 32.69. So down to 30.03, which is why I wanted to get way down to here, negative 30. And this one starts at 0 shear in my shear diagram, 0 shear. So that means it's horizontal, and then it gets larger and larger and larger values of shear. So that means the slope in my moment diagram gets steeper and steeper and steeper. So maybe something like that. And then our last little section here we're at negative 30. This is a positive 30. It's a constant shear in this section. So it means it'll have a constant slope, and it's positive shear, so it means it'll be a positive slope. So it will essentially get us back to 0, kind of like this. And so we've got this weird, now normally I say that we don't want to have discontinuities, but here we clearly have a discontinuity, but that point corresponds to where we put a roller. Well, I didn't draw it on here, but point B is like a roller. So this is kind of like a diving board with some weight on the back of it to hold it in place, and then 6,000 pounds on the end of it. And you could see where this beam would make this odd S-shape type thing where the distributed load between A and B is trying to push it down, and the point load at 6 is also trying to push it down, but it's on the opposite side of this roller at B, so it's having to do a weird S shape to make this work. So the beam is having to do something like, that. And so this point at B does transition from tension on the bottom of the beam to tension on the top of the beam, and that's why you get this weird discontinuity in your shear diagram, or in your bending moment diagram. So this one, you go through here, and your maximum bending moment is this negative 30. So M max is negative 30 kip feet. All right. Now we can take this information along with, wherever I put it, this allowable stress information, and figure out what S needs to be. So earlier we said that sigma max, or sigma allowable, in our case, is M over S. This would also be M max, I guess, to be clear about that. So let's take that equation, but let's use it as sigma allowable. So you could think of it as sigma maximum allowed. Sigma allowable equals the maximum bending moment, and it's going to be the absolute value of it, because we don't really, like I said, we do have instances where it matters if it's tension or compression, but most steels don't care if they're in tension or compression as far as their strength goes. Other materials like concrete very much care, but that's a whole different course. If you're civil engineering, you'll do a whole course on concrete beams and things like that. All right, so sigma, we're going to allow, what was it, 16,363.6. So 16,363.6 psi is allowed. We have to deal with 30,000 foot-pounds. So I just took the kips and translated them to pounds. And technically it's negative, so it will have tension on the top of the beam at that point. And then divide by the section modulus, which we are actually going to solve for. So therefore the section modulus equals, let's see, 30,000 divided by 16.363.6. Oh wait, 16,000, oh, I did that wrong. 363.6. Where's my delete button? All right. Oh, go ahead. Yeah, we probably should, because otherwise S in our chart is inches cubed, and if we have feet up here, then that's going to create problems. So 12 inches per foot, so that we end up with the right kind of units. So let's actually take 30,000 times 12 divided by 63.6. 22, pretty much exactly. All right, so what this means is that the section modulus for our beam actually needs to be greater than or equal to 22 inches cubed. And we know that we wanted, early on it said we wanted a standard flange I-beam, so that means we have to go to the chart with the S's in there, and we're looking for beams that have section moduluses greater than or equal to 22 inches cubed. So let's go over here, and, oh, not that one though. Let's look at our S, and let's start at the bottom because we want the cheaper ones, right? We want the ones that are going to hold up but not cost us that much. So S is this column. So no, these are all too small, too weak. All right, so none of those had section modulus that was good enough. They needed 22 or greater. All of these above there work. So now, so basically it's from this point up that will work for our situation. And at this point, we want to find the lightest weight beam in this list. So you have 121, 106, 70, 54, 50, 42, 35, 31.8, 25.4. That's their lightest beam. So S10 by 25.4 has a section modulus of 24.7. We only needed 22. So this one works, and it's the lightest of the available beams. So we would say that at S10 by 25.4, can't write that, S10 by 25.4 beam will work the best. And in our case, best equals lightest weight, which we assume equals lowest cost. And we're going to assume that lowest cost, which works, is the best thing. May not always be, but it's a good starting point. And we have eliminated all these other beams that do not meet our criteria of having the factor of safety at 2.2. Yep.
So when you were making a little graph diagram thing, why when it was going from 0 to 2.66, why did it curve like this instead of curving like this?
So, oh, you know what? Let's see. Oh, well, so we need to look at it bigger. So let's go down here. So the shear at that section was this little triangle. So this was what the shear looked like in that section. It started at 4 and it went to 0 kips. So that was the shear force in that section. So remember the moment diagram, the slope of the moment diagram is basically based on the shear plot. So I guess the slope of the shear, or the magnitude of the shear, not the slope. The magnitude of the shear is the slope of the shear of the moment diagram at any point. So I have, it's not a big number, it's 4, but a lot of times it's easier to start with the low number, because you know the low number, in this case the low number is 0, and you know that 0 shear equals a 0 slope, and 0 slope is horizontal. So I know if I'm looking at my moment diagram down here, I know I started at 0 because it was the very end of the beam, so I started at 0. And I know where I ended because I ended, this area was 2.66. Yeah. So this area was 2.66. And if I wanted units on this, this is kips, this is feet, and so this is kip feet. And down here, this is 0 kip feet, and this is 2.66 kip feet, And I also know that at the 2.66 point, the slope, the shear is 0 at that point, which means the slope here is horizontal. So, it's kind of horizontal. And over here at the 0 point, I guess I could go and try to plot it, that the slope is 4 kips per foot, basically, and it's positive because these numbers in the shear diagram are positive. So I know that in general the slope is positive, and I know that it starts out not horizontal. It didn't really start out vertical, but it starts out something. And so I just kind of fill in the blanks that I know that it's horizontal when it gets to the 2.66 point, and I know that it starts out somewhat vertical at the 0 point, and the only way to make that curve is something like that. And when I draw it, it's really tiny, so you can't see a whole lot. And then the opposite thing happens in the next section, where the shear is all negative. So the general trend of my moment diagram is a negative slope, and it starts here with a shear of 0, which means I start with a horizontal slope there. So it starts out more or less horizontal, and then it gets larger and larger and larger. The shear does. The shear gets larger. It goes from 0 to negative 14. So it's gradually getting larger, which means that I get a steeper slope here. And I kind of drew it the right way, where the slope here relates to that 4, 4 kips per foot positive. And here it relates to negative 14 kips per foot. And so I did draw it steeper than the 4. I'm not too worried when you're drawing these things if you're getting these slopes exactly right. I do like to see that the curvature is right. So you didn't draw this, this thing, because this would say that over here at this point, you thought the slope was not horizontal. In fact, you thought it was vertical almost. And then you thought it was close to horizontal down here, which is the opposite of what's going on. So I do care about that kind of thing. I don't particularly care if you've got exactly the right slope at like the 4 kips per foot here and the 14 kips, negative 14 kips at the other end. It's more of did you get the relative slopes right and the curvature right? And again, on the exams, I'm not going to have you draw one of these things just because I can't grade that the way the exams are graded. So it's only going to show up in things like web work, where it asks you the slope between these 2 points is whatever. Quiz 3, I think, might ask questions similar to that. I can't remember. It does ask questions about drawing a shear and bending diagram. I don't remember if it asks specifically about curvature or not, though. Don't forget to take quiz 3. It closes sometime this week, I think, this coming Thursday. So that's kind of how I rationalize it. You could just go through and memorize. I think when we first did the shear and bending diagram lecture, I put up a little chart of the 4 different combinations of shear. So you have a triangle like this one, you have another positive triangle that goes from 0 to a big number, and then you have the 2 negative ones and the corresponding slope or shape curvature in your moment diagram. You could just memorize them, but they are able to be rationalized also. You don't have to just memorize them.
So let's say the triangle backwards split.
Yeah,
so curvature would be the opposite?
So let's look at the 4 different options. So you have, this is your shear, B equals 0. This is it. And for the positive ones, there's this option and there's this option. So in your moment diagram, well, we won't draw that, but in your moment diagram, you know that in general, both of these have positive slopes because they're positive shears. You just don't know the curvature. And so in the moment diagram for the top one, you know that it starts as 0. So that means it starts horizontal. So it starts out more or less like this, and then it goes up. The other one, it starts at some number and ends horizontal. So you know it ends horizontal, and then it goes with a steeper slope on the left side of that. And then there's 2 others, if I can get them all to fit. You have V here and maybe here. You have one where they're both negative, and the moment diagrams for these, you know that in general they have negative slopes because they're negative shears. In the first one, you know that it starts horizontal because the shear is 0, so it starts horizontal and then it gets steeper. And the other one, you know that it ends horizontal because the shear is 0 at the end of that little section, and it gets, well, it doesn't drop down like that. It, does something like that. And sometimes there are other options where the triangle doesn't actually go to 0, but you have a high end and a low end. And so I always treat the low end as it at least approaches horizontal. So that's usually the way I go about doing them. So first figure out, is it generally a positive or negative slope? So that gives you the blue line. And then figure out which end is the end that looks horizontal, or at least closer to horizontal than the other end. And start at that end and work your way towards the other end. So those are the 4 combinations that you might have to deal with. Anything else? That's all we need to do for design of beams. So anything else? The rest of the week, the next 2 lectures, Wednesday and Thursday, are going to be beam deflection.